Good evening again. It barely seems like 5 minutes that I was last here talking to you. So you've had the professional side of things, what the James Webb is doing. This is very much what amateurs are doing, the amateur being me. So, do people remember 2020? Our lives changed, possibly for the worse. Life in lockdown, where this particular object led to these objects appearing all over the floors and pavements, and it got me looking down, thinking I'm supposed to keep my distance from people, and I keep looking down at my feet. But Stephen Hawking said, remember to look up at the stars, not down at your feet. Try and make sense of what you see and wonder about what makes the universe exist. So I thought, well, I can't go to the pub and talk to my friends and socialize, so what the hell, I'll set myself a lockdown challenge. Now, we all know that the universe is vast and the universe is ancient, and we all know that large telescopes, space telescopes and large ground-based telescopes, have imaged galaxies that are billions of light years distant. And I thought, Stephen Hawking says, look up at the stars. I wonder how far I can look up at the stars. What is the most distant object I can catch? And I thought, wouldn't it be interesting to try and catch a very distant object without using a telescope, just using the camera that I have? And I asked myself, is it possible to think about some of these very distant objects, for instance, the objects we've been talking about with the James Webb Space Telescope, is it possible to capture one of those without a telescope, just using my camera and a lens? Spoiler alert, yes it is. Otherwise I wouldn't be giving you this short talk. So I went to the Astrophysics Journal and I found a bunch of professionals who had surveyed all of the very bright galaxies, very distant galaxies in the sky, these so-called quasars. There's the word used there. What is a quasar? A quasar is a galaxy with a very bright nucleus. It's assumed that the nucleus is a supermassive black hole, and because so much energy is pouring out of these supermassive black holes, these objects can be seen even at tremendous distances. So an artist's impression, we don't know what they actually look like because they're all so distant, but maybe that's what a quasar would look like close up. A black hole which we can't see, producing an enormous amount of energy. If matter is falling into the black hole, enormous amounts of energy come out, and some of that energy is in the form of ultraviolet or visible or other electromagnetic radiation. So I looked at this survey and thought, I want to photograph one of these. How are we going to do it? So I looked at this list of all the objects they had found from previous surveys, and I looked for one that would be visible from the UK, because they're all over the sky, some of them aren't suitable. This is the summer of 2020, so I wanted an object that's visible from the UK, preferably very high in the sky. I didn't want to start photographing things over the tops of roofs. I wanted something as high in the sky as it's possible to get. So I found one particular object in this catalogue where the professionals had found an object which is visible for us in the UK during the summer nights, and it's at an enormous distance. They had taken a spectrum of this object, so we had an idea of how much the light had been stretched, so we have the redshift. I'll say in a little while how we convert redshift into distance. So the spectrum, I don't suppose it's a particularly interesting looking spectrum. All that matters in the spectrum of this particular object, this particular quasar, this is the blue end of the spectrum, that's the red end of the spectrum. Astronomers tend to use angstroms rather than nanometers, so 4,000 to 7,500 angstroms is the same as 400 to 750 nanometers. All that's important in this particular case is they identified this particular peak, for reasons I'm not going to go into. They identified that peak at 6,500 as belonging to a radiation peak that should appear at 1,200 if the object was static. It's been stretched because this object is moving away from us because of the expansion of the universe. So that peak at 6,500 has actually been shifted from 1,200 angstroms. And redshift, the quantification of redshift is how much has it been stretched compared to the original value. So it's been stretched by 53, the difference between 65 and 12. It's been stretched by 5,300 compared to its original 1,200. That gives you a redshift of 4. Hence, on the left-hand side, the redshift of this object is 4.3. So I'm taking this from these professionals who know what they're doing. I've said, right, this object whose coordinates are given, its name is effectively its coordinates. It doesn't have a name otherwise. And I know this is a very distant object, and we'll come to the distance very shortly. All we have to bear in mind at the moment is a redshift of 4 is a very remote object. That's all we care about. So I decided to take my camera. I have a Nikon DSLR camera. I put a telephoto lens on it and then put it onto a star tracker. I use an Ioptron sky tracker. Other trackers are available. A tracker is basically just a box that will turn the camera at 1 revolution per day. So in this case, there's a little polar scope in the corner. So as long as you line it up on the North Pole, it will turn the camera at 1 revolution a day. And because it's lined up with the Earth's axis, it should keep the camera pointing at a distant object. I used a Nikon DSLR camera and a 300mm lens. A 300mm lens, that's my lens of choice when I decide to go to Africa and take pictures of animals. That's the lens I use. This is not dedicated for astrophotography. This is very much the camera and lens that I use when I go on safari and take pictures of lions or zebras or other animals in the wild. The telephoto lens itself is not that large. You can see here it's barely 150mm in length. It's 6 inches for those who prefer old money. So the lens itself fits in the palm of your hand. So it's not a particularly long telephoto lens. And the question I was asking myself is, well, that's the camera and lens I use for wildlife photography. They are not customized, they are not modified. It's not a camera that's been modified for astrophotography. It is absolutely bog standard, a daylight camera. If it works for taking pictures of zebra, and I know it does because I've used it for years, does that same combination of camera and lens, is it possible to take an image of a quasar on the other side of the observable universe? So that was the challenge I set myself. So I know the coordinates of this object because I looked it up in this survey, and this is the one I found that was nice and high in the sky. This is the middle of summer. We don't have much of a night in the middle of summer. I only had a few hours between the end of evening twilight and the start of morning twilight. But I knew that Draco was high in the sky, so I picked this object, which was a redshift of 4.3. This object is sitting in the constellation of Draco. There's Ursa Minor just next to it, and of course there's Polaris at the end of the Ursa Minor asterism there. The little rectangle there shows the field of view of a 300mm lens. The dot in the middle is not the quasar. The quasar is much fainter than that. The quasar is a magnitude of about 17 or so. There just happens to be a magnitude 5 star close by, close in the sense of in the sky, not in terms of distance, of course. The star is very close, the quasar is very distant. But just by chance, the quasar happens to be on a line of sight not too far away from that star. So I lined up on that star, knowing that if the star is in the middle of the field of view, I will have hopefully caught the quasar as well. So I set up the camera pointing at that star, and then took the longest exposure I could get away with on a summer night. And on a summer night, I figured the longest exposure I could do would be 2 or so hours. I didn't take one long exposure, as many of you astrophotographers know. What you tend to do is to take a series of shorter exposures. This has a number of different advantages. Not least, clouds were scudding by, and some of the images were lost. I just simply told the camera to keep taking images, and some of them were nothing because clouds came in. I was taking this image of the camera on the tracker, was outside my front door. There was a street light not far away. I had a wheelie bin in between the camera and the street light to try and throw a bit of shadow. My neighbor had a security camera which came on from time to time. Possibly a cat came through. When the security camera came on, I lost that frame. So I took about 2.5 hours worth of frames, threw away the ones where the security light came on, threw away the ones which had clouds scudding by, and that left me with about 2 hours worth of exposures. When you add them all together, it's roughly the same as a 2-hour exposure. The bright dot in the middle is, again, not the quasar. That's the 5th magnitude star, 80 Draco. That was what I effectively lined up to. Some of the other stars in this field of view are 8th magnitude, and I actually focused on those. It's easier to focus on a faint star than it is on a bright star. It's easier to tell when a fainter star is in focus. So I focused on those, lined up on that, and then figured, right, if this has worked, and if the quasar is where I think it is, according to its coordinates, then the quasar ought to be in the middle of that square there. So I took the image after stacking them all together to get my 2-hour exposure. I zoomed in on that particular square. And right bang in the middle of that square is the quasar. I double-checked that the coordinates of that point, according to plate solving, is exactly where that quasar is. I haven't confused it with a star. That is quite definitely the quasar, the galaxy with a very bright nucleus. We're not seeing any spiral arms of a galaxy. We're only seeing the nucleus because it is so bright. Essentially, all the light from that quasar has gone into something like 1 pixel in the image. If we blow up the quasar right in the middle there, it still doesn't look particularly spectacular. Aesthetically speaking, it's the most boring astrophoto I've ever taken. But all of the light, pretty much all of the light, I've just made this a little bit brighter. You can see some stars in the background, some very faint stars in the background, but essentially all of the light from the quasar, at least 80 or 90% of the light, has gone into that central pixel, and only a tiny amount has gone into the surrounding pixels. So it might have been a 20 megapixel camera, but only one of the pixels is important as far as I'm concerned, because that's the one that has caught the quasar. Just a little aside on what we might expect in terms of, right, if we've got a lens of a particular focal length and a particular aperture, the laws of physics tell us there's a limit to the smallest thing you can possibly resolve. Diffraction limits the size of the star or quasar that you can possibly resolve. For a 300 millimeter lens, which is f4, meaning the front element is about 75 millimeters in diameter or so, the laws of physics say you will not resolve anything smaller than 9 microradians, millionths of a radian. Astronomers prefer arc seconds, so that means the lens is capable of resolving a little bit less than 2 arc seconds. What about the camera itself? The camera has a spacing on the pixels, and when we work that out, we find the pixels are separated by about 15 microradians, or about 3 arc seconds. So if the lens is perfect, I'm not claiming Nikon make perfect lenses, but assuming there's no serious aberrations in the lens, then the lens is capable of putting all the light in 1 pixel, because it should be possible to put all the light into about 9 microradians, or 2 arc seconds, and the pixels are separated by about 3 arc seconds. So yes, it ought to be possible to put all the light into 1 pixel, so perhaps that's no surprise. Just for sort of comparison, if we were to imagine the Milky Way galaxy at the sort of distances we're talking about, then the Milky Way would be a few pixels in size, maybe a couple of pixels or so. So we are talking about even the Milky Way galaxy would hardly be more than a pixel. So it's no surprise that the nucleus of this galaxy is not filling multiple pixels in the image. If we return to this particular image, just as an aside again, I was interested to see what else was in this particular crop. This is an 8 arc minute by 8 arc minute crop of the original image, and by comparing with the database of galaxies, I actually found that there's actually a few other galaxies in this image, apart from the one I was trying to get. Now, I admit that you can't tell those are galaxies. You have to trust me that I've looked up these things and they are galaxies rather than stars. Some of them you can perhaps tell because they are not circular. They seem to be slightly elliptical. This one and perhaps that one seem to be stretched. Anything that's perfectly circular looks more like a star, but some of the faint ones are galaxies as well. So I actually caught about 10 galaxies in that 8 by 8 arc minute, which is of course just a tiny crop of the whole image. So given that there's nothing special about that particular crop, I think there's maybe 7,000 galaxies in the entire image itself, which is why I'm calling it the Barrett Deep Field. Not quite as good as the Hubble Deep Field. The Hubble Deep Field caught as many galaxies, but of course in a much smaller area of sky compared to the rather large area of sky that I'm assuming here. So it is possible to catch the light from this very distant quasar, but how distant is distant? The one thing you can measure is the redshift, but then it's a bit tricky to go from the redshift to, yes, but how far away is that? What is the distance to this quasar? Well, you can imagine the quasar or galaxy, let's use the words interchangeably because a quasar is just a galaxy with a very bright nucleus. this galaxy has emitted some light, and there was a certain distance between us and the galaxy when that light was emitted, what I call the distance then, the distance when the light was emitted. And then as the light is on its way to Earth, of course, the universe will continue to expand, because that's what the universe does. It has been doing for 13.8 billion years, and as far as we can tell, will continue to do so. So as the light is traveling towards us, the galaxy gets further away, and eventually the light reaches us, and of course the galaxy will be further away again. So when the light reaches us, we can say, well, that distance is the distance the galaxy is now, the time when the light actually reaches us. So when we talk about the distance, do we mean the distance when the light left? Do we mean the distance when the light arrived? Or do we mean how far the light has traveled? Those are three separate values for the distance. And therefore, if ever you read somewhere in a book, a magazine, a web page, the distance to the galaxy, you could argue it means nothing unless you specify which of these three distances are you actually talking about. That's made even more awkward by the fact that if we think of this one, how far has the light actually traveled? That's even trickier than it sounds, because whilst the light was traveling through space, space was changing. The light was traveling through space at the same time that space is being stretched by the expansion of the universe. It's a bit like trying to swim through water at a particular speed, but the water is flowing. Maybe if the water is flowing faster than you can swim, you end up going backwards even though you're trying to swim forwards. It's also like saying, well, what if an ant was moving along a rubber band, but whilst the ant was walking along the rubber band, some joker was stretching the rubber band. So how far has the ant actually walked? You can't simply say, well, it was there and it's now there, so it's moved that distance, because the ground on which it is walking, the rubber band on which it's walking, is continuously changing. And we're not generally used to that idea of everything under our feet continuously changing. We're used to the idea that the distance from Liverpool to Chester is fixed. Whatever it was yesterday, it's the same as what it is tomorrow. The universe doesn't work that way. The universe is continuously changing. So the only way we can answer the question, how far has the light traveled from the galaxy to us, is to have some knowledge of how the universe has been expanding. And we do have an idea. In other words, we have a model that says we think there's this much matter in the universe, we think there's this much energy in the universe. If that's right, then the universe has been expanding like this. We have a model that tells us how the universe has been expanding. And if we have a model, a mathematical model, then we can say, for a given redshift, how far away was the galaxy when the light left, how far when the light arrived, how far has the light traveled. We can calculate those three distances for any redshift as long as we understand what the universe is doing. So I put the relevant formulae into a spreadsheet and came up with these three lines. So these are red, green, and blue. Red is the distance to the galaxy now, green is how far the light has traveled, and blue is the distance when the light left the galaxy. Notice, on the scale here, notice that these are basically tens of thousands of light years, and this is the redshift across the horizontal axis here. Small redshift means things are very close. So if we're talking about a galaxy which is, let's say, only 1 billion light years away, and on this scale, 1 billion light years is next door to us, it's not the other side of the universe. If we're talking about a galaxy which is relatively close, notice that all these three colors are effectively the same line. If the galaxy is relatively close to us, then the distance when the light left and the distance when the light arrived, the universe has hardly had any time to expand. So those distances are all the same distance. But if we're talking about a very remote galaxy, it takes billions of years for the light to arrive. The universe has had plenty of time to expand in the meantime. And so these three colored lines start to separate when we go further and further and further back in time to larger and larger and larger redshifts. Now, this particular galaxy, we are told by this survey from professionals who know what they're talking about, they say, according to the spectrum of this particular object, it has a redshift of 4.3. So we can read off the curves at that particular value and say those are the three distances which we could say are the distance to the quasar. Let's just get rid of the curves because they're just getting in the way at the moment. Those are the three numbers we're interested in. Let me remind you what those three numbers mean. The quasar was roughly 5 billion light years away from us when the light was emitted by the quasar on its way to Earth. It has taken 12 billion years, 12.4 billion years for the light to arrive. Remember, the universe is 13.8 billion years old, so it's taken 90% of the age of the universe for that light to actually arrive here on Earth. And because the universe is continuing to expand whilst the light is on its way to Earth, the quasar is now at the incredible distance of 25 billion light years away. This is, of course, all calculated, assuming we understand how the universe is expanding. But when we look at those numbers, apart from the fact that they are mind-bogglingly big numbers, in the 12 billion years that the light has been traveling, the distance to the quasar has gone up from 5 to 25 billion light years. It's changed by 20 billion light years in a time period of 12 billion years. So a little back-of-the-envelope calculation tells us, well, this is interesting. Its distance has increased by 20 over a time period of 12. If we do a simple calculation of the average speed, distance over time, its distance has increased by 20 billion light years, and it's taken 12 billion years for that to happen. So its speed of recession is 1.6 times the speed of light. It's receding from us on average over the time period we're talking about by 1.6 times the speed of light. Not only that, but we can, if we wish, do the calculation and say not only that's the average, can we actually work out what the speed was as a function of time? And yes, if we understand how the universe is expanding, we can actually calculate that. And I did that and found that the recession velocity as a function of time, so the blue dot is when the light left the galaxy, and the amber dot is when the light arrived in my camera. Notice that it started when it was receding from us at more than twice the speed of light. So even though the light was trying to get towards us, it was actually in space that was moving away from us at twice the speed of light. And as you might expect, as the universe is expanding, the expansion seems to be slowing down. That's pretty much what you would expect. Gravity tends to pull on things. So as the universe expands, gravity will slow the expansion. But this is the surprise that caught everybody by surprise. After a little while, it started accelerating again. In other words, the universe did slow down in its initial expansion. But for the last few billion years, it looks like the universe has changed gear and is now accelerating its expansion. This is something we did not know about more than about 25 years ago. It was assumed that this curve would simply drop continuously. But now we realize this curve seems to have dropped, and now the universe is expanding and accelerating. The curve is now going up. A big, big surprise. But notice at no point did this quasar ever recede from us at less than the speed of light. It started at a recession velocity of twice the speed of light. It dropped to about 1.5. It then has accelerated a little bit. On average, it's about 1.6. It's always been it's always been receding from us faster than the speed of light. And yet the light still made it into my camera. That really is weird, and it takes an awful lot to get your head around, mainly because we are not used to thinking that way. We think of Liverpool to Chester as being a fixed distance. We don't think of distances changing as a function of time. If you had to get from Liverpool to Chester but the distance kept changing, then how on earth does the train ever get here if Chester keeps receding away from Liverpool? This is not something we're used to thinking about, which is why it sounds so weird. Let me show you what we think is going on and what's actually going on. This is time here. So there's the Big Bang, and this is us now, 13.8 billion years later. This is distance from us. So we think when the light left the quasar was about 4.5 billion light years from us. Now the light that is currently hitting that screen as it's going towards your eye, you would assume the light is getting closer and closer and closer and closer to your eye. As a function of time, light is simply moving from the screen to your eye so that you can interpret that light. But for this quasar, we might think that's what's happening. Surely, as a function of time, if the light is left here, then surely it's going to get closer and closer and closer. As time goes by, as we go up the scale, surely the light is going to get closer and closer and closer to us. No, the universe is expanding, and the universe is expanding faster than light. If the universe is expanding faster than light, light cannot travel faster than light can travel through space. It is a fixed speed. 300,000 kilometers per second is a fixed number. It cannot go any faster. Space can expand faster than light, but light still has to travel through space. So if space is expanding at twice the speed of light, the light goes backwards. The light from this quasar is trying to make it to Earth, but space is pulling it away from Earth. You can see what actually happens for about 2 billion years. After the light has left the quasar, we can ask, where is the light now? And the answer is, it's further away than when it started. It was originally only 4.5 billion light years from us. But 1 billion years later, it's a little bit more. It's about 5 or maybe 6 billion light years away from us. So as time goes by, the light is actually getting further away because it's being dragged backwards by the expansion of the universe. Eventually, a few billion years after it leaves, eventually it starts making some headway and eventually makes it to us here and now, 13.8 billion years after the Big Bang, something like 12.5 billion years after the light left the quasar. That, again, is so weird, it takes time to think about. So if your head is starting to hurt and if your brain is coming out of your ears, don't worry. That's perfectly natural. You have to sit down and think about it over a cup of tea or perhaps a pint, and then it'll start maybe to make sense. But this is really weird stuff. What is happening to the quasar itself? Well, as the light is getting dragged backwards, the quasar is simply getting carried by the expansion of the universe and is getting further and further and further away from us because the universe is just continuing to expand. Now, strictly speaking, it shouldn't be a straight line. Remember, I've just showed you that the speed of recession is actually changing. So that straight line there implies that the speed is constant, which it isn't. So that should be a slight curve. I can't work out exactly what the curve should look like, so I've just shown it as a dotted line. But the quasar is getting further and further and further away from us, such that by the time we get to now, the quasar is over in the top right-hand corner, something like 25 billion light years away. So that really does take a little bit of thinking about. But I think it's interesting just to think about the light itself. The fact that it's getting dragged backwards is weird, but just think about it from the light's perspective. The light was emitted by the quasar about 1.4 billion years after the Big Bang, when the universe was only 10% of the age it is now. It had been traveling for something like 8 billion years, even before the sun and the earth existed. The sun and the earth were born, and then it continued to move for another 4.5 billion years. Life evolved on Earth. The light traveled on. Dinosaurs came and went. The light traveled on. In the last million years of its journey, the light will have arrived at the edge of our Milky Way, crossed a few spiral arms, and end up entering the solar system. In the last few hours, it would have arrived at Earth, and it would have taken only a fraction of a second to come through the atmosphere, hurtle towards England, dodge a few clouds, and go through the lens and hit the camera sensor. It's only 1 pixel in the image I took, but what a journey that photon has had, or collection of photons. So as a graphical summary, I decided to set myself the challenge of put a camera on a tracker, point it at Draco, where I had hoped to find a quasar on the other side of the observable universe. I took the image, which is the main image shown here, blew up that small little square, and found the quasar is indeed imaged by the camera and the telephoto lens. So in answer to the question, is it possible to capture something from the other side of the observable universe with just a camera and a lens, not a telescope? Yes, it is. I've captured what I like to think of as this quasar's ancient light. Thank you all for listening.